So it's my pleasure to introduce Zhizhang Xie, and he will talk about a stable version of Gromov's angle shrinking problem and its index theoretic application. Okay, Zhizhang.
Okay. Well, first, I want to thank the organizers for the invitation. Um, so today, I want to talk about a stable version of Gromov's angle shrinking problem and its index theoretic application. Mainly, this index theoretic application is uh, to prove an index theorem, and then it's used to prove the Gromov dihedral rigidity conjecture. Sorry, my voice is a little my nose is a little bit stuffed today, so I hope you can hear me okay. If you have any questions during the talk, please feel free to ask. Um, okay, so let's get started. So I will first introduce Gromov's angle shrinking problem, which is the following. Take a convex spherical polytope. The question is, does there exist a continuous deformation of this convex spherical polytope through a family of convex spherical polytopes, which are which have the same combinatorics of the original convex spherical polytope, which we call Y0. So start with the Y0. You want to deform it through YT. All of them have the same combinatorics. All of them are convex spherical polytope. Now, the key condition here is throughout the deformation, all the dihedral angles of YT will be bounded by the, bounded above, I should be more specific, bounded above by the corresponding dihedral angles of the original Y0. Okay, so every single YT is compared to Y0. So here's a picture. And in the end, you deform and deform, and then it shrinks to a point. Here's a picture. You start with, this is I guess, a two-dimensional spherical polytope. So the picture is three-dimensional. You start with a picture like this, and then you deform, make it smaller. The point is these dihedral angles are going to be no bigger than these corresponding dihedral angles of the original one, and you deform to this one, and you still compare this to that guy, okay? It's possible through the deformation, the dihedral angles of these two, you don't really compare them, but it's about comparing all these guys to the original guy. And throughout the process, all the dihedral angles here, of course, is no bigger than the original dihedral angles. And in the end, if you can do this all the way to a point, that's the dihedral angle shrinking, the angle shrinking problem of Gromov. So now, so today, my main goal is to explain how this seemingly just also combinatorial or geometric problem, which is spherical or Euclidean, if you call it, why it enters into index theorem of convex polytopes, or index theorem for manifolds with a polyhedral boundary. That's what my goal is, to explain that. Now, in fact, to be precise, what we really need, in fact, turns out in the index theorem that we prove, is not quite the original angle shrinking problem. In fact, is in some sense of a dual version. It's an angle enlarging problem. So it goes like this. Start with the same, a convex spherical polytope. Now, the question is, can you continuously deform Y0 through a family of YT? All of them, again, have the same combinatorics of the original Y0. Now, the question is, the key property, again, here is you want to keep the dihedral angles always at least uh, greater than or equal to the corresponding dihedral or the original y0. And if you can do this all the way to make y0 into the hemisphere instead of a point. So instead of going to a point, you go into a hemisphere. Now, here's a picture. You start with this one. So you make it a bigger, and you make it a bigger, and then until you all the way, you reach to the hemisphere. So this is the version actually we're going to need in the index theorem computation. Now, so before I go into how this appears in the index theoretic computation, let me just briefly mention, I think Jinmin is gonna, in his talk, he's gonna talk about more details of this problem and then some of the proofs of what I'm going to say right now. But let me just mention that in dimension two, I mean, you have a spherical polytope in a two-dimensional sphere. Then in this case, Gromov's angle shrinking problem or the corresponding angle enlarging problem has a positive answer. This can be done geometrically. Or here's a special, so that's a dimension two case. In general, if you say higher dimensional case, if you have a convex polytope in a sphere of dimension three or higher, the original angle shrinking problem or in all the corresponding angle enlarging problem right now is still open in its complete generality. But in the special case that if the spherical polytope is simple, then it also has a positive answer. Here, simple means the spherical polytope, they only have, when you have two faces meet, they always meet at a codimension two face. So when you have if it's a k-dimensional polytope and you have two codimension one faces, which is k minus one dimensional faces, you have two of them. If they meet, they have to meet at a codimension two face. So in particular, this is simple. In this case, actually implies this combinatorially, it has to be a simplex. Okay. A simplex or I guess more general, a simplex cross with a cube. It has to be, yeah, it has to be of that form. So in this particular case, if this convex polytope is simple, then the Gromov's angle shrinking problem has a positive answer as well. Okay. Now, so since I mentioned about, as I said, yes, these Gromov's, this angle enlarging problem itself in complete generality actually is open. But I will explain later, for the index theorem we're trying to prove, actually, we don't need the actual geometric version of this angle enlarging problem. What we really need is a stable version of an algebraic version of this problem, which I'll explain in a few slides. Okay, so it turns out that version, that stable algebraic version, actually is true in full generality. Okay, and that's why, and that's how it's used in the index theoretic computation. All right, so let's move ahead. So since I'm talking about, there's a distinction between simple polytopes and non-simple polytopes. So let me take this one slide to explain, just to fix some terminology. So when we have a a simple corner in Rn is a region that is enclosed by exactly n hyperplanes that passing through the origin. For example, as this picture shows, in R3, a typical picture of a simple corner is exactly this corner that's closed by three planes that's intersecting at the origin. That's what we call a simple corner. Now, in general, if in Rn, if you have L hyperplanes meeting at the origin and the number of hyperplanes is greater than n, then we call it a polyhedral corner. For example, a picture like this. This is in dimension 3, you have 4 hyperplanes meeting at a vertex. So the key difference, I guess, that, for example, as far as the angle shrinking problem or the angle enlarging problem, that is concerned is because for simple corners, all the angles that you see are all the faces that any two codimension 1 faces, when they meet, they exactly meet at codimension n faces. For example, in this picture, when two planes meet, they meet at the line. In this picture, you have four faces here. For example, these two faces, they meet at a line, but for example, this face and this face here, they meet, but they meet only at a vertex. So that's the distinction. So now we introduced the simple corner and polyhedral corner. So let me just take one more slide to fix some terminology. So I think in the literature, sometimes these two notions of manifolds corner and manifold with a polyhedral boundary sometimes are mixed. So for this talk, I want to just say, when we say a manifold with a corner, we really mean a manifold with it's a manifold with bound. It's a manifold whose charts are modeled exactly based on R. It's an n-dimensional manifold, and the charts are exactly R n minus k cross a simple corner. So this is actually, in a strict sense, this is what usually people, in a classical definition of what the manifold with corners mean. So the corner structure is always simple corner. Now, for more general corner structures, for polyhedral corners, actually, let's use the terminology that it's a manifold with a polyhedral boundary, which means the chart structure is based on R n minus k and cross P, and P is a general polyhedral corner. Okay, that's the distinction. Okay. So far, so good. Any questions about the terminology? Okay, so that's just some terminology. Okay, so again, let me just emphasize the distinction between the manifold with corners and manifold with the polyhedral boundaries is really when the two codimension 1 faces meet. So here, let me just recall the definition of dihedral angles. So what is a dihedral angle? A dihedral angle is the angle between two codimension 1 faces. When they meet at a codimension 2 face. If they meet at a codimension 2 face, then we say they form a dihedral angle. So in this picture right here, so there are 4 faces. So this face and this face, they meet an edge, so they form a dihedral angle. When this face and this face will meet, they do meet at a vertex, but they don't form a dihedral angle. Okay, so that's just to clarify what we really mean, what kind of angles we're considering. Okay. So yeah. All right. So now let's get to the index theorem. So the main point of the index theorem is to prove the following Gromov's dihedral extremality rigidity conjecture. which let me just remind ourselves what this conjecture is. So there is a general version of this conjecture, but for the purpose of this talk, let's take this just convex polyhedral in Rn, which is already a very typical, it captures all the essence of the arguments already. So now let's take a convex polyhedral in Rn. Let G0 be the Euclidean metric on P. Now, suppose the conjecture says, suppose you have another metric, which is another Riemannian metric on P. Suppose you have the scalar curvature comparison and the mean curvature comparison of the faces and the dihedral angle comparison for adjacent codimension 1 faces, which is this. Then the extremality says, then the scalar curvature of the new metric also has to be 0. The mean curvature for the faces of the new metric also has to be 0. And actually the dihedral angles for the new metric has to be the same as the corresponding dihedral angle of the original metric. The rigidity says, in fact, the new metric also has to be flat. Okay, so that's the Gromov's dihedral extremality and rigidity conjecture. Now, so this conjecture now it's confirmed. It's true in this form. It's complete generality. Now, so with Jinmin, this is a joint work with the Jinmin and the Guoliang. So we show, yes, Gromov's dihedral extremality and rigidity conjecture is true. So in this work, we show that G is Ricci flat. In a follow-up work with Jinmin, we actually show this somewhat stronger conjecture, what Gromov called the flat corner domination conjecture, which says, in fact, G is flat, or the codimension 1 faces are also flat. In fact, the new metric and the old metric, G0, they are locally isometric. I should mention, subsequently, Brendel and Brendel 1, they give actually alternative proofs of the above theorems in the following special cases, where the case where the corresponding angles are equal, and the second case where the dihedral angles are acute. Okay, so now I should also mention previously, before our work, Gromov himself, of course, in the paper, traced back to 2014, he by using a gluing and a smoothing argument, he showed the dihedral extremality conjecture actually holds for the standard Euclidean cube, for example. Later on, Chao Li showed the dihedral rigidity conjecture for some special convex polyhedra in dimension less than or equal to 7. The dimension restriction is because he used the minimal surface method. And also, he also used, under some extra assumptions on the dihedral angles and the combinatorial types of the convex polyhedral. Okay. Now, so now let's get to, I guess, the main part of this talk is how Gromov's angle shrinking problem, or more precisely, the angle enlarging problem, the corresponding angle enlarging problem, how it enters into the proof of this, our proof of the conjecture. Now, so the proof of this Gromov's dihedral rigidity conjecture we use is proved by a new index theorem on manifolds with polyhedral corners. So the angle enlargement problem enters as a key step of the proof of this index theorem. So now let's be precise. So what index theorem we are proving here? So again, it's a similar setup. Let's take a convex, Euclidean convex polyhedral P with the Euclidean metric G0. Now suppose G is another Riemannian metric on P. Now suppose D is the Dirac operator on the spinor bundle of this spinor bundle. The spinor bundle here is the tangent bundle of P with respect to the metric G, and the tangent bundle, it's a direct sum of these two bundles. So the both metrics are involved, of course. Now, subject to the following boundary condition, the boundary condition says here this notation just means this spinor bundle carries a Z2 grading, and this is a Z2 grading on this spinor bundle. And here this notation, these two notations mean that this is the Clifford multiplication of the this is, let me just say, this is on some codimension one, for each codimension one phase of Fi. So for on each codimension one phase, this Vi is the inner normal vector of the codimension one phase with respect to the original metric. Sorry, I guess let me correct myself. This is the inner normal vector of this phase with respect to the new metric. And this notation means is the inner normal vector of the phase with respect to the original metric. Okay, so there are two inner normal vectors with respect to, according to the two metrics. So this is the Clifford multiplication of these two inner normal vectors on this spinor bundle. Okay, so now on the boundary condition is this operator here acts on the section when you restrict it to this boundary, then the value of this section, it should satisfy this linear equation. So that's the boundary condition, okay? Now, with this boundary condition, so, and of course, for people who are familiar with manifolds with elliptic operators on a manifold with a smooth boundary, for example, in order to make sense of index theorem, you usually need to put a boundary condition on the boundary. So here is similar. Of course, we don't have a smooth boundary. We have a boundary that has polyhedral corner structure, but we also need to impose a boundary condition. Of course, now the key condition here, in order to make sense, the index problem is the following comparison condition for the dihedral angles. The dihedral angles of the new metric is strictly less than the dihedral angles of the original metric. Here, because we're assuming it's convex, so the original dihedral angle, of course, is less than pi. So the angles are bounded between 0 and pi. So now here we have the strict comparison inequality. Now, of course, you might be thinking, well, the original conjecture of Gromov of the dihedral extremality and rigidity conjecture, we are not assuming strict inequality. We're assuming an inequality of less than or equal to. I will get to that point a little bit later. But for the index theorem, let's stick to the strict inequality for the moment, okay? And I'll explain how to reduce the proof actually to an index theorem that satisfies this type of condition. Okay, so let's keep that in mind. But for now, let's work on this index problem. And for the index problem, although for the Gromov's original conjecture, there's dihedral angle comparison, there's scalar curvature comparison, there's a mean curvature comparison. Now, notice that for the index theorem, though, the scalar curvature comparison or mean curvature comparison is not so important. Actually, it's not needed. What's really important here for the index theoretic computation is only the dihedral angle comparison. Now, with this dihedral angle comparison for the adjacent faces, of course, now with this boundary condition, so the index theorem says the Dirac operator with this boundary condition is an essentially self-adjoint Fredholm operator. If it's a Fredholm operator, of course, now the index problem makes sense. It has a Fredholm index. So the Fredholm index. So now another second key step of the index theorem, of course, once you know it's a Fredholm has a Fredholm index, you need to compute the Fredholm index. So it turns out in this particular case, the Fredholm index is exactly the Euler characteristic of this convex polyhedral. And we know that for the convex polyhedral, the Euler characteristic is 1. So the index is 1. So this is the key index theorem we need to prove Gromov's dihedral rigidity conjecture. So let me outline the strategy of the proof of the index theorem. So 2 parts, of course. We need to prove that it's Fredholm under the dihedral angle comparison. That's the first step. Once you make sense of the Fredholm index, then you compute the Fredholm index. Okay, of course. Now, let me just mention, Let me just mention that for the first step, which means to show that it's actually Fredholm, the proof is going to work simultaneously for manifold with corners or the general case of manifold with polyhedral boundaries. So for the first step, in other words, for the first step, Gromov's angle shrinking problem or the corresponding angle enlarging problem does not come in yet. As for the essential self-adjointness and the Fredholm, this first part, I've talked about this in this seminar before. So the emphasis of this talk will be on this second part. So how do we actually compute the Fredholm index and how exactly Gromov's angle shrinking problem enters into the proof? Okay. All right. So let's make, I mentioned about a few minutes ago that Gromov's angle shrinking problem or the original angle enlarging problem itself, as far as I know at the moment, is still open in complete generality. So really, as I said, what we really need is not the original geometric version. What we really need is, for the index theorem to work, is in a stable algebraic version. So now, let me explain how, what is this algebraic version and how somehow this geometric version becomes, why is sufficient to just use an algebraic version of this angle enlarging problem. So here's the key observation. So remember in this index theorem, there's a boundary condition. So the boundary condition is, let me write it down again, where VI is, this inner normal vectors of faces, right? And this is the inner normal vector of the faces according to the 2 different metrics. Now, so this, of course, if you're really thinking about inner normal vectors of these faces, then of course, we are really thinking about the shape, the geometry of the actual space. But it turns out for the boundary condition, once you write down the boundary condition, it turns out the boundary condition continues to make sense, even if for here, the particular VI originally is supposed to be the inner normal vector of the face Fi according to the original metric. But it turns out even if Vi is just some other vector, which has nothing to do with the inner normal vector of the face, it turns out this boundary condition still makes perfect sense. So now, which means we can forget about inner normal vectors. Let's just think about just take a random vector. And it turns out the corresponding angle, dihedral angle comparison condition, you can translate that into a inner product comparison. So now this is just an algebraic condition. So which means what I'm trying to say here is you can forget about the geometry of P itself. You just need to remember there are some vectors. Originally, they're inner normal vectors, but in the index theorem itself, you are allowed to change these vectors. And in this deformation process, you don't need to always specify these vectors, Vi, to be the inner normal vectors of some geometric shape. Okay, so this, which means we're translating a geometric condition into a linear algebraic condition. Okay, so that's the key sort of observation, that you go from geometry to somehow an algebraic problem. So let's remind ourselves again, what's the angle enlargement problem? So in angle enlargement problem, you have a convex spherical polyhedron. And then, for example, I have a picture right here. So really, if you are thinking about dihedral angles and really changing the shape of actual geometric shape, then what we really need is to keep track of these inner normal vectors. So you have in this picture right here, you have 4 faces. Each face has its own dihedral, its inner normal vectors. And then there's some convexity condition involved. So really, let's translate it into an algebraic condition, which is really saying, well, the convexity is just saying, in some sense, okay? This definitely is, I'm talking about a weaker version, a version that's weaker than the geometric version. What's really here that captures the convexity is you have a unit vector from the center of the sphere, for example, pointing into the interior of this polyhedral. And this is the inner normal vector. Sorry, this is a vector that's has the inner product with each of these inner normal vectors is positive. So it's a vector like this. And then I should pick a subset of this set right here, which is to indicate this set is to keep track. Here, there are some of these vectors are considered to be adjacent. For example, V1, V2 are adjacent, but V1, V3 are not adjacent. So I need to specify a subset to keep track of the adjacent vectors or adjacent faces. So now let's translate this geometric problem into the following algebraic problem. So which, in other words, the algebraic angle enlargement problem is the following. I have a set of vectors, unit vectors, and I have specified a set of adjacent vectors, what I call it, adjacent vectors. And then for this set of vectors, can you continuously deform this set of vectors so that in the end, because we're trying to make it into a hemisphere, so which means when you change it into a hemisphere, they will all go to the same vector. Let's be specific, they're all going to go to the vector n. A key property here is the dihedral angle comparison is the one that replaces, the inner product comparison is exactly the replacement of the dihedral angle comparison for the original angle enlargement problem. So this is the algebraic angle enlargement problem, which is strictly weaker than the original geometric problem. The point is here, you are only deforming the vectors. Now, it's quite possible throughout the deformation process, for some t, these VIs, when you consider, if you really want to think of them as inner normal vectors of some hyperplanes, this new set of hyperplanes might not form a convex polytope anymore. Or even if they form a convex polytope, the combinatorial structure might be different. from the original convex polypole you start with. But as I mentioned, for the boundary condition, you can forget about the convex polytope, but the combinatorics, you can forget about the combinatorics. You only need to keep track of the vectors and what are considered adjacent. Okay, so this is the algebraic version. And this has the advantage that it makes the problem easier, has a better chance to be true, I guess. Now, strictly speaking, even this algebraic angle enlargement problem, right at the moment, is still open in this form. Now, so I guess we say luckily for the index theorem itself, actually we don't really need this algebraic angle enlargement problem. What we really need is the stable version, because for the index theoretic computation, you can just cross some extra intervals and so on and so forth. Actually will make this problem easier. And that's I hope to explain. Now, before I get to that point, maybe now it's a good time to, I said, for Gromov's dihedral rigidity conjecture, it is true, the angle comparison. So for the moment, let's assume we have proved by using so let's take it for granted for the moment that by using an stable version of this algebraic angle enlargement problem, we prove the index theorem I just said. Okay, I'll get back to that. But now let's take a moment to say just a couple of slides to explain Gromov's dihedral rigidity conjecture that we prove if we take the index theorem. Now, how do we get back? Because for the index theorem, we do assume the strict inequality, but how do we get back to the original condition, which is the dihedral angle, which is non-strict comparison, right? So here's the trick. So for the proof, what we can do is we take the original dihedral rigidity conjecture. Now, it's possible that at some places the dihedral angles, they are equal, the comparison. Now, we can approximate the original target space. We can artificially, geometrically speaking, so we're going to do this algebraically, but geometrically speaking, we can artificially raise the dihedral angles of the target. So that then you will have a strict dihedral angle comparison. So now we can have a sequence of approximations, and which makes this operation better and better, closer and closer to the original. So geometrically, in order to do this, if you can enlarge all the dihedral angles, this would actually require so I guess it's not, at least intuitively, it's not hard to imagine. This would require the angle enlarging problem geometrically to be true. If you want to do this, if you want geometrically enlarging every dihedral angles of the target. But like I said, in the index theory computation, luckily, we only need a stable version of the algebraic problem. So I will come back to this. So now suppose this is done, then for each approximation, we have proved the index theorem because now it's strict. So for each approximation, you prove the index theorem, but the index is 1. So for each approximation, you have a non-zero solution for the Dirac operator with the correct boundary condition. So now, but approximations are getting better and better for this sequence. So you have a sequence approximation. For each approximation, you have a solution. So now we can prove an approximation lemma that under the original comparison conditions of the Gromov dihedral rigidity conjecture, actually, this sequence of solutions will actually converge. The key point is it will converge it's not only converging in L2, weakly, of course, it does converge. Actually, it converges in H1, in the Sobolev space H1, to a non-zero solution of the Dirac operator of the original original problem. And that's how you get that solution. Okay, so if we take this for granted. Oh, by the way, I don't think I probably don't have time to explain this approximation lemma, but in Jinmin's talk, he will give the full details how this approximation lemma works. Okay, so now once you have this solution, now it's not so difficult. Imagine by using the standard Bachner, Lichinarovich, Weizenberg, Schrödinger type estimates, you will get an estimate like this, and you go through the computation that you will see that the scalar curvature is going to be the same, mean curvature is going to be the same, and then you do some further linear algebraic computation, you're going to have the dihedral angles the same. And for the stronger version of the flat corner domination conjecture, you actually prove for various, you can change the boundary condition and you obtain a family of sufficiently many linear independent solutions. And you prove the metric is actually flat. Okay, so now let's actually, how many minutes do I still have?
Oh, I think you have like maybe 7, 8 minutes.
Okay. So with the remaining minutes, I hope to really explain now. So it's really about, so I said, it's really about this index theorem. So now let's see how this this angle enlarging problem comes into the computation of the index theorem. So for the index computation, computing the Fredholm index, it goes like this. So here I draw a two-dimensional picture, but the strategy works in higher dimension. You just need to do it inductively for each level or singularity. Okay, so but this is the typical situation. So we want to compute a manifold with some corner structures, or polyhedral corner structures, and in fact, we don't know how to compute the Fredholm index directly when you have a corner structure like this. But it's a classical theorem, or in fact, or more recently, a theorem of John Lott that in an index theorem like this, if you have a smooth boundary, then you do know how to compute the Fredholm index. So now the strategy is, can we reduce a singular situation that has a corner structure like this to a manifold with smooth boundary? Okay, so this now intuitively, maybe now it kind of, at least heuristically, you see that, well, I mean, some deformation is needed, and through the deformation process, the angle enlarging problem is going to enter. So now precisely how does that work? So the index theoretic computation works like this. So since the difficulty is caused by this corner right here, so let me actually cut out this corner. So now, it's a cutting pasting. It's more or less standard cutting and pasting type of techniques in index theoretic computation, that when you have a manifold and if you cut along a hypersurface like this, and of course there are some details to work out, which is worked out in our paper, that when you cut like this, both pieces here, the index, because the dihedral angles or the comparison still works. So for each piece right here, each individually, the Fredholm index still works. And it's a gluing formula that shows that the index here plus the index here is equal to the index of the original guy. Okay, that's the first step. It's a cutting and pasting argument. So of course you would say, by doing this, yes, you could say this does not really reduce the difficulty of the problem because you're cutting into two pieces, but the singularity is still there. Now, here's the key observation. It is true, take this piece out, strictly speaking, we still don't know how to compute the Fredholm index of this space directly. But the key observation here is through this deformation process, through the process, we're actually going to prove with the correct deformation, we can deform a situation like that with strict angle comparison, strict dihedral angle comparison. We can deform it through geometrically, roughly speaking, okay, is through this angle enlarging problem. We can deform a situation like this to a standard case. What do I mean by standard case? To a standard case, which means because originally we have two shapes. We have the shape F. We have two corners, two polyhedral corners. Two polyhedral corners, but they have different shapes. They have different shapes. So if this angle enlarging problem is true geometrically, then this deformation process would allow me to change G through this deformation process while keeping the Fredholm index the same to a standard case, which means G become the same as F. And now it is when it's in the standard case, actually you can compute the Fredholm index by hand, which turns out to be 0, okay, in this particular case, which it turns out to be 0. And now if you can do that, which I'm going to talk about in the next slide, then you can now do the same process, now take another shape, which we have already smoothed out the shape, and do the same deformation process for this piece right here, because this index and this index, we're not talking about, so we're not deforming this piece to that piece. We're talking about the index of this piece is the same as the index of this piece. And then once you know that this index is the same, then you can glue this piece back into the original manifold. And now the index there, use a cutting pasting argument again, you get a new manifold with a smooth boundary, but has the same index as before. So this is the index theoretic computation. Okay, so here, what I said here in the previous slide is roughly, through the angle enlarging problem, I can deform these two polyhedral corners, one to the other, while keeping the Fredholm index. Again, in the detail of this step, Jinmin, I think, is going to talk about this in more details in his talk. So, of course, I mentioned before, the original geometric angle enlarging problem is still open in its generality. Fortunately, luckily, in the index theorem itself, we only need a stable algebraic version. So the precise detail of, I've explained what algebraic version is and what does it mean by a stable algebraic version. Jinmin will talk about that in his talk. So in the maybe last minute, sorry, can I have one more minute? So in the last minute,
Yeah, sure.
I will just quickly explain that why in the standard case, I said when these two corners are exactly the same, why does it help to compute the index? Well, in this case, actually, is a computation by hand. If these two pieces are exactly the same geometrically, then, and you do the Bachner type of estimates, just write it down. So all the terms here, because exactly the same, they will all just be exactly, everything is exactly going to cancel out. Okay? So you're going to have a term like this. The Dirac operator is going to be greater than actually the connection applied to the section. So if you have this, which means if you have a solution of the Dirac operator with the correct boundary condition, you are going to have a solution that is parallel. If you have a parallel, then you go back and check the boundary conditions. Oh, by the way, I forgot to mention, on this cutting hypersurface here, the boundary condition here is you take to be the orthogonal complement of the original boundary condition. Okay, so that's the usual, when you do the cutting pasting, this is a usual boundary condition you pick. And then you check it. You literally check it by hand. Then with the boundary condition, if the solution is parallel, well, the solution has to be 0 in order to match the boundary conditions. So, well, which means there is no non-trivial solution. So which means the operator is invertible. If it's invertible, it has to have index 0. If it has index 0, then the nearby guys, the approximation, the nearby guys also have to have index 0. And that's the approximation step. Jinmin probably is going to talk about in more details. And that's how you do the index theoretic computation. It's reduced to a standard case. Okay, so now, and this is exactly what the step, the algebraic version of Gromov's angle shrinking problem enters. All right, thank you.